Hi, welcome to part 11 of my series on how to build your own 6502 single board computer. This episode is going to be a little longer. I'm going to talk about the glue logic and decoding of addresses on this device. And I have mentioned before um, that I map the ports to the 0 page. So this grid here of 256 values is the 0 page in Hopper, the 0 page allocation of the, what Hopper uses the 0 page for. And the light blue at the bottom is the parallel port and the serial port here. And I picked up a bit of flack for doing this, like you're wasting valuable 0 page space. You don't need to do fast stuff on, ports and all that. But that's not entirely true. Like I can, because I've got the map to the 0 page, and this being this regular 6502, if I open up and show you the instructions of the Western Design 65CO2S, suddenly you got a whole bunch more instructions. And most of them are these RMBs, SMBs, BBSs, and BBRs. And what they mean is reset memory bit 1, reset memory bit 0, and these are the 7 bits of a 0 page address. This instruction takes a 0 page as an operand, 0 page address as an operand. Reset, set bits, branch if the bit is reset, in other words, branch if the bit is 0, branch if the bit is 1, right? So with these instructions, consider that you might want to bit bang I2C on two of the pins in your parallel port. With these instructions, you can have very dense code, both faster and smaller, for doing things like bit banging I2C on your port. Anyway, my interrupt handlers are super tiny and super fast and they don't use registers. So you don't have to push and pop registers in the interrupt handler if you're just looking at the status flags in a port register using the bit instructions and branching. So it makes for much easier, much tighter interrupt handlers because you don't have to use the A register, and smaller code. Anyway, I've documented this a bit on my Hackster page when I first started doing this a year ago. I'll put a link in the description to that motivation. Having said that, it doesn't make our board terribly useful for people who are trying to run code that's being targeted at other platforms where the I/O ports are more conventionally mapped usually into ROM space somewhere. And what you probably didn't notice when I first turned this on is that says Benita I/O. And in addition to that, so what this is actually the memory map of this is like a Benita computer right now. So it's not putting the ports on the VIA and the serial port are not on the 0 page on this board. They're at the same position Benita has them, which is at hex 6000. And I've done the same. The 0 page one is my original. And I've done the same for the X16 Commander. And I should soon be getting the parts for my MECB 6502, which goes in this. It goes in this back plane. This board should arrive like this week, and I'll do another. Obviously, I'll get this to work, and then I'll also get the same mapping to work on my device, because there's benefits, right? So this is Ben's glue logic. These TTL chips here, which map the ports and his memory to so the ports are basically mapped to hex 6000 somewhere in there, and he's used TTL chips to do it. So what does this mean? It means that we can now build Hopper to run on Ben's breadboard computer. So there's two sides to this. The one is Hopper can now run on Ben's breadboard computer, and the other side to it is that software that's been ported to run on Ben's machine can now run on this machine. So, for example, there's already a basic port, so we could probably without much trouble. In fact, I'll probably try and do it. take Ben's basic port and get it running on this board with his glue logic. Anyway, nice step forward. So how does this work? Well, the file I've got up here is not a 6502 file. It's a microcontroller file for RP2040 files. And this is how you make Hopper code work across a variety of RP2040 files. All you do is you include the board definition for the board you're currently targeting. So in this case, Seed Studio board, and it basically gives you all the Arduino is pretty similar. You get board definitions like what are all the GPIO pins called on your board, and does your board have features like I2C, etc. Here board has I2C, board has a NeoPixel, etc. So what I did is I took the same approach, not that file. Let's find a regular Blink. Okay, I took the same approach here for 6502. So if I want to build Blink for the Benita board, I include this file. And in this file, it's showing us where his port A and port B are. It only does the ports because the main definition is actually you've actually got to rebuild the firmware for this too. You can't just rebuild your Hopper code. You have to rebuild the firmware to support a different because you've got to put different you got to put a different program on the PLD as well. But this is how you do the switch in the Hopper code. You just simply say I want to use I want to use the Hopper regular with the 0 page mappings, and then in here all your ports are bytes. Whereas if we're using Benita's board, then our ports are UINTs, they're words. Also, let's have another look at another one. This retro, the retro board is a board, also another New Zealand board by Dave, but his mapping is similar to the X16 Commander, so that's where his ports are. Okay, let's go and have a look at the firmware and see how it works in the firmware. Because you would need to you already need to, earlier in this series there's a episode on how to build your firmware, how to build your ROM, right? So it's in the runtime for source runtime, and it's runtime 6502, right? So at the top of the firmware, you have to define, if your board is not the generic 0 page version, then you have to define something like that to say I'm using the Benita board, or I'm using the X16, right? The X16 board. And let's see what that does. There's lots of definitions here. Like you can say I don't have I2C on my board, or I'm using a different serial chip. In fact, you do have to use a different serial chip for the 6502 retro board. All it does is it sets things in the 0 page here. So if we look in this file for X16, there we go. So if you haven't defined a board, it'll automatically default to the 0 page one. And then like for the X16 board, for example, there's different port assignments depending on whether you're, what serial chip you're using. But you can see here they're assigned and they're UINTs. There we go. And then if you've got a regular 0 page board, then the ports are bytes. If not, they're UINTs. And I do this on purpose because this Hopper 6502 assembler that is used to build this is type safe. So it'll spot a mistake if you try and use a 0 page instruction with a UINT address, and it'll give you a compilation error. So it's a good way to check that you're not trying to use 0 page instructions. Now let's go and have a look at some of the code and how it differs depending on which one you're using. Like, for example, let's look at the serial. We'll look at both ISRs. So if we go and look at the ISR, so the interrupt service routine for serial. So you can see here, the majority of times it's going to get straight past these two ifs and return. And this interrupt service routine is going to do nothing. It's going to be very quick. So it's using these bit instructions, the branch if set instructions. And then I do have to use the A register here because I'm taking what's in the data register and putting it into the serial buffer. So the ifdef here is like if you are using the 6502S instructions, which these exist, and I added this, and if you've got 0-page IO, then do this. Otherwise, it just does, for all the other ones, it uses the same code that it would use if you didn't have a 6502S. So the sort of longhand instructions, and now you're pushing and popping your accumulator. You can do this. You could do the top one here with the bit instruction, because the bit instruction takes the top 2 bits, but it doesn't help you that much because in the next step you're going to have to look at the next instruction, and and it's not the top 2 bits, so it doesn't help you so much for checking the bits on this port. You can only get so far with the bit instruction. For the parallel port, I think you could have used the bit instruction. I don't know if I do, because I used all these. I do use the bit instruction here for this one. And all the parallel the VIA is doing on the service routine is it's updating the tick count for the timer. It's this fires every millisecond, I believe, and it updates my 32-bit tick count. So I do use the bit instruction for the non-65 CO2S version and the non-0-page version. I use the bit instruction to. Ooh, yeah, that'll work, because the bit instruction works on a 16-bit address as well as an 8-bit address, as well as a 0-page address, and I use it more than one time. Yeah. Whereas these BBS instructions would only work on the 16-bit 0-page address for those two. Yeah. So I use them where possible. I mean, I do use the regular bit instruction. Okay, anyway, so there was a bit of that sort of code to add and go through, and I had to add a feature to the compiler as well, because my 6502 assembler doesn't really have the equivalent of a .org or origin like instruction to say this needs to go at this address. So what would happen is it's generating code, and if this is in the same position as where the ROM is, which it might be, code will be generated right over that address, and you'll get a bad image. So I added a new sort of directive to the Hopper 6502 assembler called reserve, and so it'll reserve 256 bytes at that address, and that means when it's generating code as it arrives, as it arrives before it arrives at this address, if it's generating code for a method that overlaps this address, it then just stops, puts in a whole bunch of no-ops, and starts generating after the reserved space again, so that you don't get a collision between your code and your ports. So this was my workaround, but actually I like it this way. It's much, I like it this way, but it's obviously not as flexible as a .org instruction. Yeah, because the other thing I did is and we're finding that this is a bit limiting. I specify memory size with ROM here, these ROM instructions, and I try and squeeze it into 16. And what this means is that, like 32, 16, whatever, it assumes that you want that memory to end at FFFF, with the 3 vectors at FFFA. That's 6 bytes worth of vectors sit up there, and then your ROM is snugged up to that top address. And with the 6502 retro board of Dave's, it doesn't really work, because he's banking ROM, and he's banking ROM in a location other than where I'm assuming it is. So we're having to do sneaky things to make this assembler still work for that. So I don't think my adding the reserve directive is going to really solve that problem completely. I'm going to have to do a little bit more work on it. Anyhow, where do you find this stuff? So if you go to the Hopper repo under the CPLD folder, which is under project single board computer CPLD, these PLD files are the program for your PLD, and in the I've got pre-built JED files for various different ones, and then I used this in the earlier episode to show you how you don't need to use WinCuple to, WinCPL to make these. You can just use the pre-built ones. I haven't made pre-built ones for these more recent ones, like the BE one is the Ben Eater one. So here you can see the Ben Eater, that doesn't actually look right. It's supposed to be 6000. Maybe I'm wrong about 6000. I'll verify. Anyway, I decided not to do pre-built versions of these yet because it's starting to get out of hand because there's more than one CPLD you've got to do the pre-built versions for now. So it's easier just to do just the regular board, and then if there's traction, I think if you want to do if there's interest, if someone doesn't want to install WinCPL and they ask me specifically for a target like for Ben's one, I'll just do it quickly, and to whichever chip you're using, whichever GAL you've got, whether you've got a 8 macrocell GAL or a 10 macrocell GAL. Anyway, but for now I'm just going to leave it this way. I am going to verify that I got that right though, because this comment just looks wrong. Yeah, all right. So we can now try and see if we can get software that's been designed to run on other memory maps to run on this board. So thank you for watching, and enjoy trying to get some of the basic versions running up on this. I'd like to see BBC Basic running on it.